lectures. This is the fourth and final subunit of the first unit of grade 9 chemistry, the atomic models. Now this unit is actually very interesting because it's like the basement, the foundation of all chemical concepts after this. Okay, so because it's so important, a lot of people have tried to define, over the centuries, have tried to define what the atom actually looks like. The first person, who you may be familiar with, who came up with the first atomic theory, is Dalton. Now, Dalton's model, he called it the billiard ball model because he thought atoms were just a solid ball, basically, a billiard ball, like pool. Anyway, so in his model, he had no idea about the subatomic particles, but we know better. We know about the subatomic particles. We know about protons, neutrons, and electrons. So did J.J. Thomson, and he came up with the second atomic model. This atomic model he called the plum pudding model because I guess it's some British thing, where you have your pudding, and inside the pudding you have like plums. He thought of it as the pudding being the atom, and plums being the subatomic particles, or the positive and negatively charged particles just like floating around inside the pudding, in a sense. But next we have Rutherford, and Rutherford is the one that discovered the nucleus. So he knows that the atoms aren't a solid ball, they're actually mostly empty space, although there's this dense central nucleus. He knows the nucleus is positively charged because we have protons and neutrons. Neutrons have no charge, which leaves this positively dense central but small nucleus. And he knew that there were electrons orbiting in some way around this nucleus. His downfall was he didn't know how they were orbiting around the nucleus. But fear not, because we have Bohr's model. Now, Bohr's model gave a very specific way of how electrons move around the nucleus. He gave them shells and energy levels, and he made it in a beautiful system that we actually still use today. The final is the quantum mechanical model. We found out that there's more, there's a deeper understanding, there's a deeper passageway of how electrons moved. It's not as easy as just pointing out a shell and saying that an electron is found there. But today, we do use Bohr's model and the quantum mechanical model to best describe the atomic models. Who knows, we might go into a further understanding of atoms, but this is what we have today. So let's go into detail about Bohr's atomic model. So you can see here that we have this dense central positive nucleus, and we have shells around this nucleus. And you can see that each shell is designated with a certain number. These numbers, 1 through 6, are called principal quantum numbers, and they are represented with this n, right? And each number, each level, is not just a shell. It's also an energy level, and it's also an orbit. Now, the whole point of these orbits is carrying electrons, right? So, Bohr's atomic model gives an exact number, a maximum number of electrons that each shell can hold. He uses the formula 2n squared. So if we were to see this individually, the first shell could hold a maximum of 2. In place of n, you simply put the quantum number, the principal quantum number 1, and you square it, so you get 2. The first shell can hold a maximum of 2 electrons, no more, all right? But it can hold less, but no more. The second shell could hold a maximum of 2 times 2 squared electrons. That would give you a maximum of 8 electrons. Similarly, the third shell could hold a maximum of 3 squared electrons, 18. All right, so it goes on and on and on like that. But you see how each shell has a maximum number of electrons. I say maximum, like I said earlier, because it might be minimum also. Electrons like to move around, right? And when they do move around, there's a lot of energy changes that happen. For example, let's say there's an electron in the first shell, and it jumps up to the 6th shell. This is why you have to understand shells are more than just orbits, okay? They're energy levels, okay? So if I were in the first shell, a low energy level, and I tried to go up to a 6th shell, a much higher energy level, I need energy. So this kind of movement of an electron absorbs energy, right? So you can think in the opposite way. If I'm at a higher energy level, 6 for example, an electron comes back down to the second shell, for example, this kind of movement will release energy, all right? So in Bohr's model, it's more than just a shell, it's also an energy level that you have to consider when thinking about this atomic model. Next, we have the quantum mechanical model. So what makes the quantum mechanical model an improvement from Bohr's mechanical model is that new concepts were discovered, okay? The first concept is the concept of sublevels, okay? So we had the principal quantum numbers, we had the levels 1, 2, 3, 4, 5, 6, but then beyond these levels, there were sublevels, which were designated with SPDF. And it goes further on. Even further than these sublevels, there's even more orbitals, which are within these sublevels. And these orbitals are where electrons may be found, okay? It's a difficult concept to understand. But even through all these divisions of levels and sublevels and orbitals, we're still not exactly sure if electrons will be found there. So you say that orbitals are places where electrons are probably found, or they may be found. It's difficult, it's a little difficult to wrap your head around this concept, but just know that beyond levels, there are sublevels, and beyond sublevels, there are orbitals. So to wrap up all these new concepts, I have two tables here, okay? The first table are some concepts we know, that there are energy levels, and here we have 1 through 4, and each of these energy levels you can designate with a symbol also. So in place of 1, you can say K, in place of 2, L, 3, M, and 4, N, all right? It's just a simple way to represent the principal quantum numbers. And now we also know that there are sublevels also, 4 sublevels, S, P, D, and F. But each energy level has a different number of sublevels, okay? The first energy level has 1 sublevel, S. The second has 2, S and P, the third has 3, SPD, and the fourth has 4, SPDF, okay? So what do each of these sublevels mean? Well, like I mentioned earlier, each sublevel has orbitals, which are where the electrons actually may be found, okay? So the sublevel S has 1 orbital, and we know 1 orbital can hold a maximum of 2 electrons, okay? P has 3 orbitals, and we know that 3 orbitals mean that there's 2, 2, 2 in each, a maximum of 6 electrons. Don't be confused with orbits, okay? So this is what people usually get mixed up with. Orbitals are different from orbits that we saw in Bohr's atomic model, okay? Orbitals are like the final place. They're these elliptical shapes or areas where electrons may be found, and each orbital can hold a maximum of 2 electrons, and each sublevel has a certain number of orbitals. Moving on, we know that D has 5 orbitals. Each orbital can hold a maximum of 2 electrons, so the whole sublevel D could hold a maximum of 5 times 2, 10 electrons. Finally, F, just like that, we have 7 orbitals. Each orbital can hold a maximum of 2 electrons, giving it a total of 14 electrons. All right. This is a lot to take in, right? So if you can memorize this table, good for you, honestly. So I came up with an analogy, all right? Or a kind of easier way to reference the quantum mechanical model, maybe in order to understand it better, okay? So first I'm gonna go through the 4 things that we have to know in an atom, okay? We have to understand an energy level, a sublevel, an orbital, and then electrons, okay? Let's start with an energy level, okay? Think of an energy level as the floor of a school, and let each floor represent an energy level, okay? So we're focusing on energy level now, right? Let's draw it like this, okay? It's not anything fancy, but just imagine that this box is a school, and each floor of the school represents an energy level. The next thing we have to discuss is sublevel. Now let sublevel be a classroom, okay? Now, in the bottom floor, you see that it's blue now. In the bottom floor, let's say we have 1 classroom, okay? This 1 classroom, labeled in blue, let this be the sublevel S, all right, for the sake of an analogy, okay? So the bottom floor, the first level, has only 1 classroom. The second floor has 2 classrooms, a blue and a green classroom, or S and P classroom. The third floor has 3 classrooms, S, P, and D, or the blue, green, and red classrooms. And finally, the fourth sublevel, the fourth floor, the highest energy level, has 4 classrooms, blue, green, red, and yellow, okay? And this would be S, P, D, and F, okay? So I hope you understand so far that each floor, consider it as an energy level, and each classroom, consider it as a sublevel. Finally, we have orbitals. Now, think of orbitals as desks in the classroom, okay? Each classroom can only hold a specific number of desks, okay? The blue classroom, or the S classroom, can only hold 1 desk, okay? So all blue classrooms can only hold 1 desk, okay? Remember, consider desks as orbitals. So now moving on to the green classrooms. The green classrooms, maybe it doesn't look like it here, but the green classrooms, let's say they're a little bit bigger. So they can hold a maximum of 3 desks, okay? So each green classroom has a maximum of 3 desks, all right? 3 desks each. Next, we have the red classroom. The red classroom, again, is a little bigger, and it can hold 5 desks, right? So the red classroom can hold 5 desks. Kind of running out of room here. 1, 2, 3, 4, 5 desks. Finally, we have the yellow classroom. The yellow classroom, the biggest and the special of them all, can hold 7 desks total. So 1, 2, 3, 4, 5, 6, and 7. All right, so to recap, we have a school. In this school, each floor has a certain number of classrooms, and each type of classroom has a certain number of desks. The first classrooms, the S classrooms or the blue classrooms, can hold only 1 desk. The green classrooms or the P classrooms can hold 3 desks. And the red classrooms or the D classrooms can hold 5 desks. And finally, the yellow classrooms or the F classrooms can hold 7 desks. Now, we're reaching the last concept. So the final concept is electrons. Now, consider electrons as students, because this is a school. We're missing students here, right? So just understand this. Every desk, no matter where it is, no matter which floor, no matter which classroom, every desk can hold a maximum of 2 students, okay? This might take me a while to draw, but let's say that every desk can hold a maximum of 2 students, like this, okay? I'll be back once I've drawn all the students. Okay, and we're back. That took me a long time, but you can see here, if you can see here, that every desk can hold 2 students, right? But think again, you're a student yourself, right? Are you always at your desk? No, you should be, but you may not always be at your desk. You might stand up and go talk to your friend, or you might go up and eat lunch, or go to the bathroom, or whatever the case is, you as a student must know that you aren't always on your desk. Similarly, electrons aren't always in their orbitals. So electrons aren't always sitting at their desks, okay? They like to move around too. But the quantum mechanical model and this school model tries to show you that these electrons should be at their desk. These electrons should be at their orbitals, in their respective classrooms, in their respective floor, right? So I hope this analogy helps you understand a little bit what quantum mechanical models is. What the quantum mechanical model is. You might have to relook at it again, and if you want to use the table, you can use that too, or come up with your own analogy too to help you understand the quantum mechanical model. So that is the end of the first part of the fourth unit of grade 9 chemistry. It's a pretty large subunit, so I wanted to divide it into 2 parts. Stay tuned for the second part of the 4th subunit of the first unit of grade 9 chemistry.